This is a good overhead view in the area where the underground connector is going to be constructed. I just want to sketch that in for you. The underground connector will be constructed in this area. And obviously it cannot be built under the existing pavement. The solution is to shift the roadway as much as possible to create an open workspace where the underground connector can be constructed. What you see here is an area of temporary asphalt being prepared to shift that traffic. With the temporary asphalt in place, the 6 lanes of existing traffic can be shifted as far to the west as possible. The shift will occur 1 lane at a time, so you probably would put 1 lane in service, and after that you can put the 2nd lane in service. If the new temporary asphalt is at the same elevation as the existing roadway, it's fairly straightforward to move the lanes over. But on this project there were always differences in elevation, and they had to be accounted for. So very often you'd have to shift it a lane at a time and then make some adjustment to the difference in elevation in order to shift the next lane. That often required that the work be done at night, or the work could also be done over a long weekend. In the absence of that grade difference, the shift could take place rather quickly. Probably 1 evening shift would be enough. But given the complexity of adjusting the grades, you need to shift a lane at a time. You may need to reduce the number of lanes in service, and the slow hours of the weekend would be the best time to try to do that. You can also see this crew beginning to lay out the concrete barrier, so they are quite close to the point where they're going to open the detour. Of course, at the last minute you need to do the striping, and the striping has to be carried onto the existing pavement as well. So there's a great deal going on, much of it under live traffic. So to the extent that you could get an extended shutdown, it just makes the transfer of traffic that much easier. Here's another view of the same area, and in this photo that offset has been placed in service. So the traffic used to be over here someplace. You can see some remnants of that roadway, and after the shift they're way off to the side. You've now created this very large workspace to construct that underground passageway. So you have 3 lanes of southbound traffic in this new location. You have 3 lanes of northbound traffic in this location, and you've cleared this big area for the construction of the underpass. At the same time, the basic construction of the new highway is taking place in this zone, and off the picture to the left or to the south, that narrow band is under construction. This is the same orientation taking a short time later, and you can see the activity now with these 3 drill rigs. They are putting in the supportive excavation for that underground connector. These rigs should look familiar to you now. They're putting in secant pile walls, and that will be the means of supportive excavation for the underground passageway. It's quite deep. It's below the water table, so the secant pile wall presents a very good solution. The new highway is at a higher elevation than the existing, could be as much as 6 feet higher. Raising the grade is being accomplished using a GRES wall. That's a geotextile reinforced earth system. Because the new roadway will be at a higher elevation than the existing, you need to create some kind of a support at the edge of that new construction. There will be a sharp drop-off between the new and the existing, and that's contained by means of this GRES wall. It's extremely effective. It goes down very quickly. It's made up of a kind of a basket of wire mesh placed in combination with geotextile fabric of various sizes, and it's quite effective. In this project, it will be used for perhaps 6 foot height, but it can go much higher than that. Now I'm standing on the other side of the GRES wall so that you can see its construction a little better. There are individual layers. You can see this very heavy wire mesh, and the material is contained in place by means of the fabric. This is put down in lifts and goes up quickly. It really goes up as fast as you could spread the fill material, and produces this excellent temporary retaining wall. In this project, the fill is constructed using lightweight material. This is special material which weighs perhaps as little as 1/2 of the weight of normal soil. On this site, there is a compressible layer of soil, and if you added a 6-foot overburden, you would get a significant settlement of that compressible layer. You overcome this by adding lightweight fill instead of normal weight fill. But that in itself would add a 6-foot overburden, albeit half the weight of a normal overburden. It still would produce unacceptable results. So the solution was to excavate a quantity of the existing material and replace it with lightweight fill, and then place lightweight fill above it to reach the final grade. So you're sort of lightening the load to begin with, and then replacing it all to obtain a net zero effect. That is to say, there is no additional load per square foot on that compressible material. I believe lightweight fill also has applications as backfill behind retaining walls to reduce the load on the walls. So there's a widespread use for lightweight fill. Now the area has been brought up to grade with lightweight fill, as I've been saying, and it has also been topped off with subbase. The subbase on this project consists of a 12-inch layer of granular material. It has been placed here and rolled and compacted, and it looks like it's just about ready for the formwork. While we're here, I want to point out how the work zone is completely secured, completely isolated from the public. I just want to move from left to right and describe what's going on. This fellow is walking on the subbase. The subbase is 12 inches of granular material compacted and fine graded to exactly the correct grade. When that's in the right place, the roadway forms are placed. They're usually metal forms, and they're held in place with steel pins. On the inside of the form, there is a keyway in place to form a keyway between the adjoining slabs. Now, when the form is in place, you're ready to place a layer which we all call popcorn. It's a 4-inch layer of cement treated fine aggregate. You apply just enough cement to get the fine aggregate to bind together, but you don't want to fill all the voids. You want to have a porous mix, and this is what is obtained here. The idea of a permanent porous layer under the concrete pavement is excellent for the durability and long life of the pavement. When that 4-inch layer is in place, you can attach these dowels. You attach them with couplings, and that will allow you to couple them to the adjoining slab. And then at frequent intervals, I would guess the intervals are about 12 or 15 feet, you install these cradles of rebar. These are set at the location of construction joints. The construction joint is saw cut in later. There were many formed joints tried over the years. They all had some defect, and the latest method, the most successful method, is to pave through these bundles of rebar and then come back and saw cut over them to create a joint. That's what's being done here. Finally, you place an 11-inch layer of concrete. Now, this system is called a 50-year pavement, or sometimes it's called a European pavement. It certainly seems very robust, and I imagine the term 50-year is justified. And this is the process used here. This is a New York State DOT process. It may be totally different where you are, and of course everything you do has to conform to your local requirements. Here are the components of this pavement. There's a 12-inch underlying subbase, then there's 4 inches of fine aggregate plus only enough cement to get it to hold together. It remains very porous, and that is exactly the intent. Then there is an 11-inch concrete slab. The slab is unreinforced, and you can see here the female ends of the dowels. You will insert a male dowel, and that will join the two slabs together. The top surface is roughened with tines to give it this longitudinal scratched effect, and that produces what we call a 50-year pavement. Here's a general view. You can see where the workers are standing. 2 lanes have been completed. This would be 2 lanes of the permanent roadway, and as you come closer to the camera, there's another full lane over here, and this is a kind of a partial lane. Now, you really don't want to pour little tapered shapes. You don't want to pour a lane that's less than the full width, because in the finished product, the motorist tends to see the seam lines between the lanes, and that's what really guides him. Sometimes that is more obvious and easier to read than the painted stripes. So you don't want to create a lot of shapes which are different than the traveled lane. There's an area here which has been left out. There's a recess in the pavement on this project that marks the location of a crosswalk. So there'll be a pedestrian crossing at this point, and the pavement is treated differently. There could be granite stone laid in this area to differentiate it from the rest of the pavement. In this project, there's colored concrete that's going to be placed in the walkways. Now, 2 lanes are all you could fit in this space, but when you want to shift traffic, you will need 3 lanes. So the area where the dyno is being leveled off, and that will be covered with asphalt. So when you're ready to open this to traffic, you will have 2 full lanes, which are the permanent lanes, and one temporary lane, which is going to be asphalt. Similarly, you would have to place some asphalt in this area to create the full 3 lanes that you need. And now in this view, traffic has been shifted. So beginning on the right, this is the area which was offset. All the traffic was pushed as far to the west as possible. And now it's being redirected onto the permanent pavement where you could place permanent pavement. And that's supplemented by temporary pavement where you needed the full 3-lane width. So that slice is now placed in service, and that immediately allows you to create a new work zone, which is a new narrow strip, and you will now repeat the same process of placing as many lanes of permanent pavement as you can. You can see the edge of the GRES wall, how it's supporting the raised embankment here. It's a sharp drop off, but it's very easily supported by the GRES wall, a very inexpensive, quick way to achieve that retaining wall. I wanted to compare the starting slide with the final slide. We've been able to construct the first elements of new pavement in this area and then supplement it with temporary asphalt where we had to. In that same general area, there was a new sewer that had to go in. All of those activities had to take place. The utilities, including the sewer, and placing new pavement, plus temporary pavement. Then finally, in the bottom slide, that was open to traffic. As you can see, the duration is a little less than 5 months, which I think is excellent progress given these long, narrow shapes. You have to remember it's very hard to access them. So you're working in long slivers, you're backing the equipment in and out for the full length of these long, narrow slivers. You cannot get the normal production that you're used to getting. So I think they really completed quite a bit in being able to accomplish this first shift of traffic in less than 5 months. With the traffic shift in place, all the traffic now is over here on the left of the photo. You're now able to establish a new work zone. The machine on the right is breaking the concrete so that the slabs can be lifted out and loaded off. And then you're pretty much repeating the same cycle of doing all of the utilities, followed by the pavement, which will be followed by still another traffic shift. And that's the way you have to execute a project of this sort. You need these long, narrow work zones which are difficult to access. You need to be prepared for less productivity, higher unit prices. That's the unavoidable consequence of working in this kind of a crowded, narrow setting. Here's a close-up of the GRES wall. You can also see the edge of the pavement, all of the features there, the popcorn, the concrete layer above it. There's a little piece of black tape here. The construction joint is created by saw cutting the pavement, and I think I'll have slides of that later on in these presentations. So that creates a controlled crack right over that bundle of dowels, and that is the construction joint. That needs to be promptly filled in with some joint sealer, and this piece of tape on the end is just containing that joint sealer. The GRES wall is here, it's doing its job, it's quick to install, and it's perfect for this kind of an application. So at this point, the existing pavement will be removed. the new utilities will be installed, and the cycle continues.